皆さん、こんにちは。本日はウェビナーにご参加いただき、誠にありがとうございます。私はビトナと申します。SACS モーセスなどのオプションプロダクトのユーザーサポートをしています。Hello everyone. Thank you for joining our webinar today. My name is Bitna. I'm in charge of the user support of our offshore product, such as SACS and Moses. We recently released a new version of SACS with many updates. It is 15.1. Today, I'm going to present the functionalities of this new version of SACS. Let me start. The first update I will introduce is about the addition of new code. The American Petroleum Institute, named API, released its second version of LRFD code check. We have made this code available in SACS 15.1. This new version includes updated provisions for conical and tubular strength check. Also, it has a new formula for dented tubular sections, as you see in the screen. Furthermore, it also has an update on joint strength check. To be specific, table for strength factor QU values has changed. Also, the equations for the gap factor and code for force factor QF, they also changed. These mostly correspond with those provided in the API WSD 22nd version. Basically, they have updated API LRFD second version to align with API 22nd WSD. The next update is about specifying unbraced lengths for code checking. As we know, unbraced length is the distance between braced points of a member, and this length is used in many places such as effective length calculation or allowable calculation. Through the update, we can specify two types of unbraced lengths, one for the top flange here and the other for the bottom flange. Actually, this feature was only available when the Eurocode was selected. But for the AISC, only one brace length can be input for top and bottom flange. Sometimes this becomes very inconvenient because users have to run the analysis two times, to find the critical unity check. But now, it is extended to the AISC code check, and the post-processor will automatically use the specified bottom unbraced length if the bottom flange is in compression. This is the next update. Let me move on to the next page. The next update is about the design of the suction bucket foundation. Traditionally, SACS only supports the tubular and I-shaped sections as a pile section. And now, new type of foundation is added, as you see in the screen here. And also, interoperability with the soil finite element analysis software named Plaxis, as Plaxis 3D is added. The workflow is, first, user can model a superstructure like a jacket with a series of load cases to generate nonlinear springs. Then we can reduce this modeled system for using Plaxis. What I mean by reduced model is like a stiffness matrix and force vectors. The suction bucket model can be automatically modeled in SACS using plate elements, and also exported in readable format of Plaxis 3D. Then, Plaxis 3D read all these properties, like bucket geometry and reduced superstructure information and load vector also. And then it performs nonlinear static analysis. What it calculates is displacement of the bucket model and the soil pressures. This interoperability with Praxis is the key part of the analysis of the suction bucket foundation. The next step is SACS generate pool model. What I mean is suction bucket is combined with the superstructure and reading all the information from Praxis here. And what SACS does is to generate the nonlinear springs associated with the suction bucket soil interaction. This is through pitting process. After having these nonlinear springs, user can freely choose the type of analysis such as static analysis or dynamic response analysis, then do the code checking or fatigue check. This is the whole workflow. Now, what I mean is, after generating the nonlinear springs, users can freely run the analysis like a modal analysis and do the annual post-processing that is applies to you, such as code checking or visualization of the result or fatigue analysis. Let me show you a short video clip. Here, first we generated the SACS model and super element and stiffness matrix and load vector will be exported to the Praxis 3D, and Praxis 3D calculates the soil pressures between the wall of the suction bucket pile and the soil, and then it is imported again in SACS. Then it does the analysis and code checking. Here's the SACS model with the suction bucket. And this is a Praxis model with the suction bucket from the SACS. This is the analysis result. Reaction is visualized with colors. And SACS model with linear springs is shown in the screen now. Then after run the analysis, we can get this kind of stress result on the suction bucket. Or with this stress, we can run the fatigue analysis. In this slide, let me give you some more detail about the modeling of suction buckets. To be specific, this kind of suction bucket model is automatically generated through one of the utilities we added to this version. The name of it is Create Suction Bucket Database. And also, the result from the Praxis 3D can be imported through this Read Suction Bucket Database utility. And furthermore, as you see in the screen, those numerical values of nonlinear springs can be checked in the chart viewer. What I want to say here is the interoperability process, it is automated through our utilities. So we can minimize our manual job here. Let me move on to the next page. The next update is about the pile foundation analysis. As you may know, SACS Pile 3D was a standalone program that analyzed the single pile, as you see here on the left-hand side. For the analysis, you need to first model a single pile and input soil properties, and you also need to input loadings from the superstructure above the pile head. This process usually needs a separate analysis to catch the load from the topside from the superstructure. Now, through the update, this Pile 3D module has now been extended to read reactions of the structures on top and apply them as a pile head loading for unlimited number of load conditions. With this feature, users can perform monopile analysis using SACS model, which is suitable for wind turbine analysis. As you see on the screen, we added monopile analysis with the Pile 3D module. It needs model information and pile and soil information. So again, user input the load and the load is calculated, and the reactions at the pile head is automatically transferred to the pile 3D module. And then pile 3D module analyze the single piles here. This is the update for the monopile analysis. And let me introduce the next update. The next update is also about the pile foundation analysis. As you may know, SACS PSI module calculates the nonlinear springs from input soil properties, or user can directly input the load deflection curve. Generally, they are the axial and lateral load deflection curve. And with this information, the PSI module does the pile structure interaction analysis. And in the new version, the module has been extended to read more of the information. They are the MC theta, base shear, and base moment curves. Basically, these properties are calculated from the Praxis model, which is for the analysis of the monopile wind turbine structures. This feature is to predict the response of the large diameter monopiles because their failure mode is different with the general long and slender piles that is used in the jacket structures. Anyway, in this way, users can design the monopile structures in accordance with the PISA method. Before this feature, Pile 3D that I mentioned in the previous slide was the only capable of reading this data from the Praxis model. Let me move on to the next page. The next update is about the structural solver. As we know, for the structural analysis, structures should be fixed in a space to prevent the rigid body motion. This is a basic and fundamental assumption for the structural analysis. However, what if we have to analyze the structures moving in a space or that are not fixed? In this kind of case, we usually apply the soft and fake springs to the structures to make analysis run. For example, picture here is the substructure of the floating wind turbines, and this picture shows the structures that is being lifted. And this picture shows the jacket structures that is launched from the barge. None of them is fixed in a space. As I mentioned, in this kind of case, for the structural analysis, we usually apply the springs or give a fixed to the structures, then run the analysis and get the displacement and stress report. And now, through our update, we do not need to use this fake fixed anymore. SACS solver automatically detect and remove the rigid body motion for statically undetermined structures. Using this feature, users can perform the analysis of floating structures, as well as lifting and launch analysis, without the need to introduce the fake boundary conditions to limit the rigid body motion. So this is one of the features I like, and let me move on to the next update. The next update is about the joint measure program. As you see in the screen, before this update, joint measure tool could not model the steepers, but now it allows the user to create the steepers for tubulars. The steepers here are automatically added as members. What I mean by members is it's a beam element that has sections. All is done inside the joint measure tool. These steepers can be modeled individually using the joint measure module. And furthermore, users can also create ring and longitudinal steepers. The steeper groups can then be added to tubular members in the joint measure input file. This is the update for the joint measure, and let me move on to the next page. Next update is about the integration with Bentley's iTwins hub. SACS is now integrated with Bentley's iTwins services. For your reference, iTwins services is an open platform managing the digital twins of the infrastructures. SACS first offered integration with iTwins Design Review in version 15.0. And now SACS 15.1 offers integration with iTwins Hub through the iTwins Analytical Synchronizer. Let me give you some more detail about iTwins Design Review in the next slide. Here's the iTwins services. Bentley iTwins Design Review is a collaborative service hosted on the web that allows two or more interested parties to communicate each other in the context of a 3D model. This 3D model is the one we call as an iTwins. The iTwins services application publishes the analysis model to an iTwins design review session for an intuitive point of collaboration that facilitates the review of the design work in progress. The iTwins Design Review is integrated in Pre-Seed and Post-View and SACS Executive. Here's a picture of the Pre-Seed with the iTwins model, and this is the picture of the SACS Executive with iTwins here. Here's an example of the iTwins model on the web. This web-based interface, accessible with a web browser, offers a set of commands for navigating and checking model information. Here, you can view and clipping the model from a different perspective, and also you can measure the distance, area, and angle, something like that. And also check the physical information such as dimensions, materials, overbeam, and also the analytical information such as member fixes, applied loads, and reactions. In addition to these review tools, it also provides a very nice feature for communication with other reviewers. For example, we can leave a command for other people to review. The thread of commands can be assigned status like reserved or open, something like that. This is the overview of the iTwins services. If you want to know more about this, please send us an email. We can give you some more details. Let me move on to the next page. The last update I will introduce is the SACS API and batch processing through this script. Through this update, user can modify the model through the scripting and run the analysis. So, through the script, user is able to create customized tools such as macros that manipulate SACS model data and results. So, user can perform the parametric study without opening and revising the model file for each of the analysis. For your reference, the SACS API is exposed in three formats: C++ library, Python extension, and COM server. All functionality is available in all formats. This is all I prepared today, and thank you again for joining our webinar.